Myself Kalma, lecturer in mathematics in K.B.N college. Today I am going to teach a topic in a Discrete Mathematics 2. It is a topic for the first year second sem BVOC students. In this I am going to teach a unit 4, that is lattice theory. First, what is meant by lattice? To define a lattice, first we have to take a non-empty set. That means there should at least a single element in that set. And it has to be closed under two binary operations, meet and join. Binary operations means it have to apply the operation between two operands. Here we are using meet and join. Then the algebraic structure L comma meet comma join is said to be a lattice if it satisfies the following laws. The first one is commutative law, that is interchanging the element, that is A meet B is equal to B meet A. Similarly, A join B is equal to B join A. The second law is associative law, that means A meet B meet C is equal to A meet B meet C. And the second one is A join B join C is equal to A join B join C. And the third one is absorption law, that is A join A meet B is equal to A meet A join B. When a non-empty set with these two binary operations satisfy these properties, then the algebraic structure L meet join is said to be a lattice. And the next one is, what is meant by distributive lattice? It's just distributing the elements. That means a lattice which satisfy the distributive law is called a distributive lattice. That is, for every three elements A comma B comma C in L, we have to distribute the elements between them. That is, the first one is A join B meet C, that can be written as A join B meet A join C. That is, here we are distributing the element A with both the elements B and C. Then we get A join B meet and A join C. And the second one is A meet B join C, that can be distributed as A meet B join A meet C. That is, a lattice is said to be distributive lattice if it satisfies the distributive law. The next one is, what is meant by isomorphic lattice? A lattice is said to be isomorphic. First we have to define a mapping between two lattices. Here we are taking two lattices L and L dash and defining a mapping F. That means F is a function which is defined between L and L dash. Now F is said to be isomorphic if it satisfies the three properties, that is, first one, 1, second one, onto, and third one, homomorphism. If F satisfies these three properties, then we can say that F is a isomorphic lattice. First, what is meant by 1? For every two elements, that is, if the mapping of images elements are equal, then the elements should be equal. That is, if F of A equal to F of B, then A must be equal to B. Then that mapping is called 1. And the next one is onto. What is meant by onto? For every element in a codomain, there should exist an element in domain. Here codomain is L dash and domain is L. So in L dash, there exists, for every A dash belongs to L dash, there should exist an element A belongs to L in such a way that mapping should be equal to that element, that is, F of A is equal to A dash. And the third one is homomorphism. That means distributing the elements in such a way, that is, for every A comma B belongs to L such that F of A join B is equal to F of A join F of B. It is a function of homomorphism for join. Similarly, for the meet, F of A meet B is equal to F of A meet F of B. If F satisfies both three conditions, F is 1 and F is onto and F is homomorphism, then that function F is said to be isomorphic lattice, and it also can be pronounced as L is isomorphic to L dash. The symbol is L is isomorphic to L dash. When a mapping defined between two lattices and it satisfies the three conditions, then that lattice is said to be isomorphic lattice. By using these definitions, we are going to solve the theorems in this unit. Next, what is meant by complement of a lattice? If L is a lattice and A is any element in L, and we have to take the another element in the same set, that is some A complement. A is an element in L and A dash is also an element in L, then A dash is said to be the complement of A if it satisfies the true properties. That is, when we meet those two elements, we have to get the result 0. When we join those two elements, we have to get the result 1. Here is a mistake, that is A meet A dash is equal to 0 and A join A dash must be equal to 1. If it satisfies these two properties, then we say that A and A dash are the complements of each other. By using these three definitions, that is distributive lattice and complement lattice, we are going to prove the first theorem, that is, if L is a bounded distributive lattice, now we have to prove that the complements of that element should be unique if they exist. For that, here we are proving the theorem, that is L be a some bounded distributive lattice and A be any element in L. If suppose there exist any two complements for A, we have to prove that they are unique. Unique means, that means for every element in a lattice there should be only single complement. For that purpose, here we are taking two complements of an element A, that is x comma y. So to prove that every complement of every element in a lattice is unique, it is enough to prove that these two elements are equal. That is, suppose x comma y are the complements of A, so it is enough to show that x equal to y for the uniqueness. So since x is a complement of A, by the definition we have that if x is the complement of A, then what will the result? A meet x is equal to 0 and A join x is equal to 1. Similarly, if y is a complement of A, then A meet y is equal to 0 and A join y is equal to 1. From the definition, we wrote these two lines. Now we have to prove that x is equal to y by using these condition. Suppose y can be written as y join 0. That means y can be written as y join 0. In a place of 0, we are using here term x meet x, A meet x is equal to 0 from the x complement definition. Then we can write y is equal to y join A meet x. Already it is given that L is a distributive lattice, so we can distribute the elements. Then we get y join A meet y join x. But from the equation 2, we have that A join y value is equal to 1. That means in place of y join A, we can write 1. Since commutative law holds, we can write A join y or y join A, the result is same. So 1 meet y join x. Every element meeting with 1 results the same. That means 1 meet y join x is equal to y join x. Since x comma y are the elements of L and L is a lattice and it clearly satisfies the commutative law, then y join x can be written as x join y. From this equation, we get that y value is x join y. That can be written as equation 1 for the next purpose use. And now next one, consider x. X can be written as, similarly from the above process, we can write x join 0. From the above complement definitions, in a place of 0, we can write A meet y. That is x join A meet y. Now since L is a distributive lattice, so you can distribute the elements among them. That is x join A meet y can be written as x join A meet x join y. And from the definition of a complement of a x to the A, then we have x join A value is 1. That is 1 meet x join y. Every element meeting with 1 means definitely it results the same element. Then 1 meet x join y is equal to x join y. Therefore, from this equation, we have x is equal to x join y. From equation 1 and 2, we have x is equal to x join y is equal to y. That means x and y are equal. But what are the x and y? These two are the complements of an element A in L. That means if we take another element also, it can be equal to x comma y. That means if an element has a complement in the same set, that should be unique. That means if an element have a complement, that should be unique, that we had proved here. That means hence the complement of any element in a lattice should be unique. Hence the theorem proved. In this theorem, we had used only the definitions of lattice and complement of a lattice and distribute of a lattice. And next one, a lattice is distributed. In this theorem, we have to prove that A lattice, every lattice is distributive. Here it is given A join B meet C equal to A join B meet A join C. Now we have to prove this theorem by using that L is a only lattice. We have to prove that L is distributive. So consider the proof that let L meet join be a lattice and A, B, C are the any three elements in L. Now we have to show that L is distributive. Here from the definition we have two formulas, that is A join B meet C is equal to A join B meet A join C for every A comma B comma C belongs to L. Similarly, A meet B join C is equal to A meet B join A meet C for every A comma B comma C belongs to L. We can prove any one of the equation to prove that L is a distributive. Here in this theorem we are using the first one, that is A join B meet C equal to A join B meet A join C for every A comma B comma C belongs to L. Here it is given L is a lattice, that is meet comma join are the two binary operation and L is a non-empty set. Clearly L meet join be a lattice and A, B, C are any three elements in L. Now we have to show that L is distributive. That is we have to prove that A join B meet C equal to A join B meet A join C. So consider the RHS. What is here RHS is A join B meet A join C. Now we have to just separate the elements with the join operation. The first element is A. A can be joined with, meet with the elements A join C. Then we get A meet A join C join A, B meet A join C. Since the first part should be written as, by the absorption law we can write that A meet A join C can be equal to A. That is the first part become A and the second one is join B meet A join C. So in the third step we get the result A join B meet A join C. Here we use the absorption law since all these three elements are the elements in L and L is a lattice. And next, now we have to separate the elements in the second part, that is B join A meet C. That can be written as B meet A join B meet C. That is A join B meet A join B meet C. When the symbols are equal, then we can use the associative law. Since all the three elements are the elements of L and L is a lattice. Now then you can use the associative law. That is A join B meet A can be written in one set and join B meet C. Then from the first part, by using the absorption law we can write A join B meet A value can be A with a join B meet C. That is we have to prove that A join B meet C equal to A join B meet A join C. That is the LHS. Therefore A join B meet C is equal to A join B meet A join C for every A comma B comma C belongs to L. If three elements in a lattice can satisfy this property, we can clearly say that L is distributive. Hence the theorem. In this theorem we have used that L is a lattice and main properties we used absorption law and associative law. Thank you.